This video will cover a lot of ground. We'll give an overview of the different ways of gaining insights from data, focus specifically on gaining insights from data with the help of models, and mention the methods at our disposal there. Then we'll talk more specifically about one of these methods, gaining insights from data using model parameters, describe the simulation-based inference model, and talk about a specific implementation of this model. There are two different types of tasks that data scientists perform. The first is using predictive modeling to automate a decision or estimation process, such as deciding who gets a bank loan, distinguishing between cats and dogs, or estimating the future GDP. The second is gaining insights from data. Well, really, as data scientists, we want to learn about the people or objects described by the data. This video only focuses on the task of gaining insights from data. One way of gaining insights from data is this descriptive or exploratory data analysis. For example, calculating some descriptive statistic, making a visualization, or similar. But as we are data scientists, we are much more interested in gaining insights with some cool models, like neural networks, gradient boosting, etc. Well, unfortunately it turns out that most of these models are black box models, which means that they might make amazingly accurate predictions, but are mostly useless for gaining insights about the people or objects we want to learn about. So, is there no possibility for us to learn anything with a model? Let's look at this in more detail. All data-driven models belong to either statistics, machine learning, or AI. Now, this here is by no means an extensive list of the data-driven models. It is rather a selection of some popular models meant to illustrate the main categories of models that exist. This categorization is something I developed in order to keep track of the wide range of models that exist. One could argue about some details, but if you're interested in data modeling, this might give you a nice overview. Now, most of these models, with the exception of the relational learning, graphical and logical models, can be represented like this. The model here takes some variables as input and performs some calculations with these variables to come up with a prediction for another variable. Obviously, we want the predicted value to be as close as possible to the true value. This is done by fitting the model to the data. With a few exceptions, such as the non-parametric models, all data-driven models are fitted by trying out different parameter values and seeing for which parameter values the predictions are the most accurate. In other words, we find the best parameter values for modeling our data. So how can we use such a model to gain insights about the objects or people? What about, for example, the model predictions? They are our main focus if you're trying to automatize some decision or estimation process. Unfortunately, the predictions are not useful here, as we do not have any unlabeled data to label. For us, the predictions are therefore only a worse version of the correct y values, which we already know. One thing we can learn with the model is which of the x variables are important, i.e., which variables have a significant impact on the y variable. For this, we can use various types of dimensionality reduction, such as backward elimination. In backward elimination, we check if we can achieve similarly accurate predictions with one of the x variables missing. If the predictions are just as good without one of the variables, we have learned that this variable isn't that important. If we use a linear model, we can even test hypotheses through feature engineering and selection. Some models, most notably the rule and relational learning models, can help us find patterns in the data. The rules found by these models should, however, be enjoyed with a bit of caution. In my eyes, the absolute best way of gaining insights from data is, however, by analyzing the model parameters. Models can be considered to be a mathematical reproduction of the people or objects that are being modeled. They make their predictions by mathematically copying the real-world process that produces the y variable. The model parameters therefore directly correspond to real-world values. By learning the model parameters, we automatically learn what the corresponding real-world values are. This is very powerful. It allows us to learn pretty much any fact about the modeled people or objects, even if this fact is only indirectly observed and cannot be extracted with descriptive statistics. Unfortunately, many models are not a very realistic imitation of the real world. For instance, black box models are so called because they don't have any resemblance to the real world system. And the parameters, therefore, also have no real world meaning. Most models don't get adapted to the real world system you are modeling. You just stick in the data and press play. This is very fast and convenient. I would, however, claim that the more time we spend trying to make a realistic model, the more useful and system-specific parameters we can learn. For instance, with a Bayesian network, we specify in which directions variables affect each other. This allows us to learn some conditional probabilities. If we, however, spend the time to specify the functional form of these relations, using one of the custom calculation models, then we can learn some more meaningful parameters, such as important constants from the observed system. All these models can be very useful. When considering all models, there is, however, one that really sticks out to me as being the best model for gaining insights about complex systems. That is, simulation-based inference. For me, simulation-based inference stands out because of how accurately it models the real-world system. It really tries to match reality as closely as possible. Simulation-based inference replicates the real system by simulating everything that is happening in the real world. If we would know exactly what is going on in the real world, then a normal simulation would be the perfect model. We are, however, doing this data analysis because we would like to learn some details about the real system. Simulation-based inference allows us to specify parameters for any values we don't know. The great thing about these simulation models is that its parameters always correspond directly to the real-world values, which we learn by fitting the model to the data. The greatest advantage of simulation-based inference is that we model what is truly happening in the real world. This is very powerful. It means that we can produce more accurate models, especially if we are modeling complex systems, such as humans. It allows us also to learn real and meaningful metrics about the real-world system. Really, any metrics you could think of, including very indirectly observed metrics. This in return allows us to answer practically any questions about the observed system. And both the model and the results are very easy to communicate due to the intuitive nature of simulation. Also, like other models that do Bayesian inference, it exactly quantifies the statistical uncertainty around its parameter estimations and is very robust against overfitting. There, however, is one massive disadvantage to simulation-based inference. It takes weeks to create. It takes weeks to create a single simulation-based inference model because you have to hand-code an entire simulation just to analyze one dataset. I believe this workload is the main reason why currently simulation-based inference is not as well known as some other models. Making simulation-based inference easier to use is one of the main motivations behind the online platform Tree of Knowledge. With Tree of Knowledge, you can create a simulation-based inference within minutes instead of weeks. Creating a simulation-based model is so fast here because the online platform has a shared repository of simulation agents. To create a new simulation, you just drag and drop some existing agents into the right configuration. The agents in this repository have a set of behavior rules that makes them behave correctly in any scenario. So, if we, for example, drag and drop a politician agent into a new scenario where it interacts with two Americans, then it should behave as a real politician would. Now, creating the correct behavior rules for humans, organizations, or countries is very hard, as we do not exactly know how they actually behave. For example, a politician's attention might increase after drinking a coffee, but we do not know by how much their attention increases. This is where simulation-based inference comes into play. The platform uses simulation-based inference to learn any unknown parameter values. For example, the politician's attention increased due to coffee, by fitting the simulation to its dataset. Now here's something very interesting and cool. In the online platform, many different people have model systems involving politicians. All of these models use the exact same politician agent with the same unknown attention increase parameter. The platform can automatically learn this attention increase parameter from all of the models by fitting them to their corresponding datasets. It then combines the learned attention increase estimates from the different simulations using Bayesian statistics. The combined estimate corresponds to learning the attention increase parameter from all the different simulations at once. As is detailed in some of the other videos, learning from many datasets in this way produces very robust estimates. The platform not only allows us to learn the unknown values inside behavior rules, it also allows us to evaluate the behavior rules in the first place. We do this by replacing the existing rules with new ones, and seeing if overall the different simulations become more accurate with the agents acting according to the new rules. So, to summarize, this platform is fundamentally different to all other models. Everywhere else, we model only individual datasets. Here, we are building a generalizable model for all datasets. So, instead of modeling individual datasets, we are modeling the different agents that exist in this world and learning their generalizable behavior valid across all datasets. With the platform, we can test all assumptions and systematically improve the scientific model by evaluating different behavior rules. And we can get detailed metrics about the agents by fitting them to the data. Once we have accurate and well-trained agents, we will of course be able to use them for modeling completely new scenarios. So, the advantages of this framework are that it uses simulation-based inference models. With them, we can exactly model the true system, which makes them intuitive and easy to communicate, and allows us to learn meaningful parameters. Also, with this platform, we are building one generalizable model for all datasets, instead of modeling datasets individually. Building upon an existing model has the advantages that it is easier and faster to make, and that we can profit from other people's expertise. The model is trained on many different datasets, which makes it more robust and generalizable, and more accurate. Finally, the platform was designed as a complete, scientifically rigorous framework that allows us to validate all assumptions, propagate uncertainties using Bayesian statistics, and make predictions for new scenarios. Currently, when data scientists analyze a dataset, they have to every time create a new model from scratch. This new platform provides an alternative. They can now profit from an existing model and work together to create the most exact possible model of humans and other agents. Due to the scientific rigor of the framework, this growing model of humans and other agents is in fact an exact scientific model. To learn more about the scientific nature of the framework, click on this video. Or check out any of the other videos.